Welcome all. In today's class, we will discuss about conductivity and mobility of charge carriers in a semiconductor. So, by the name charge carriers, we mean electrons and holes. In the N-type semiconductor, electrons are the majority carriers, holes are the minority carriers. And in P-type, electrons are the minority carriers, holes are the majority carriers. So, the charge carriers in a solid are in constant motion. Both electrons and holes are at constant motion at thermal equilibrium. So, at room temperature, the thermal motion of an individual electron may be visualized as random scattering from the lattice vibrations, impurities, other electrons and defects. So, electrons or holes are in continuous motion, but the motion of these electrons and holes are in random. There is no particular pattern for that. It is random. You can see it in the figure. So, since the scattering is random, the net motion of a group of n electron is 0. So, we can't tell the same electron will come back to its original position, but it will be occupied by some other electron also. So, altogether the net motion of a group of n electrons per centimeter cube is 0. So, a single electron may not return to its starting place in a finite time. In a short period of time, this single electron won't come back to its original place. However, if a large number of electrons are considered, there is no preferred direction of flow and hence the net current is 0. So, we know how current conduction is possible in a semiconductor due to the movement of charge carriers. So, here when an electron is moving from one direction to another, an equal and opposite number of electrons will be moving in the opposite direction also. So, we can tell there is no preferred direction of flow, hence the net current is 0 under equilibrium condition. When an electric field is applied, when an electric field Ex is applied, each electron experiences a force minus Q into E. Electron is negatively charged, so we will write it as minus Q into E. If the electric field E is applied, each electron will experience a force minus Q into E. Minus Q into E. The electron accelerate in a direction opposite to the direction of field. So, you know if Ex is applied, electric field is applied in this direction, electrons will experience a force in the opposite direction and holes in the same direction of electric field. This force is too small for a significant change in the random movement. However, when a large number of electrons are taken, there is a net motion of group in the minus x direction. So, when an electric field is applied in the x direction, when we are considering for a large number of electrons, there will be a net motion in minus x direction. Now, if the total momentum of group is px, total momentum for n number of electron is px, then the rate of change of momentum is the force. We know, we have studied in our physics and all, rate of change of momentum dpx with respect to time dt is nothing but force. So, for an electron, force is minus q into ex. Right, that is given in this equation. The rate of change of momentum dpx by dt is the force, that is minus q into ex. For a single electron, it is minus q into ex. For n number of electron, it is minus nqex, where n is the number of electron. So, the net acceleration whenever these electrons in a semiconductor, there are a lot of electrons moving, right? So, whenever an electron is moving from one direction to another, there is a chance of these electrons to collide with each other. So, the net acceleration of this electron is just balanced in steady state by the deceleration of collision process. So, whenever an electron is hit by another particle, what will happen? The speed of the motion, velocity of the particle will reduce. So, that will be balanced by the deceleration of collision process. Thus, while the steady field Ex does produce a net momentum Px, the net rate of change of momentum when collisions are included must be 0 in the case of steady state current flow. So, what we are speaking is net acceleration. Due to acceleration, we have seen the rate of change of momentum is minus nqex. Now, we are going to find out the net momentum due to this deceleration force. and we are telling that at steady state there is no current flow, right? So this momentum, rate of change of momentum or force due to acceleration, when we are adding with force due to deceleration, it should be a 0. That we are now going to show. So now consider NO as the number of electrons at time t is equal to 0. At time t is equal to 0, the number of electrons are NO. And N of t is the number of electrons that have not undergone any collision at time t. When we are considering t is equal to 0, there are NO number of electrons. At a particular time t, Nt be the number of electrons that does not undergo any collision. Now the rate of decrease in Nt, at time t is proportional to number left unscattered at t. So rate of decrease in t at t is proportional to the number left unscattered. So we can write it as minus dn of t by dt, rate of decrease, right? So minus dn of t by dt is equal to n of t by tau. So this tau is known as mean free time. So in textbook you can see this tau as t bar. So in textbook and other notes and all, if you are referring, you can see this tau as t bar. This is a proportionality constant known as mean free time. So what do you mean mean free time? It is the average time before a randomly picked electron make its next collision. So an electron is present. So the time between another collision of this electron. So it is a randomly picked electron. The average time before a randomly picked electron make its next collision. So the time between a particular collision of an electron is given by the mean free time. So we got it as rate of decrease in n of t as minus dn of t by dt as n of t by tau. As collisions are random, it does not depend on the elapsed time since prior collision. So this we are not going for the solution of this particular differential equation. We are directly writing the solution. So the solution of this equation is given here. N of t is equal to n naught into e raised to minus t by tau. So the solution of this first differential equation is given by n of t is equal to n naught into e raised to minus t by tau, where tau is the mean free time and NO is the number of electrons at time t is equal to 0. So to find the total rate of momentum change from collision. So we have seen momentum due to acceleration we have seen. Now we are going to see momentum due to deceleration, that is due to the collision process. So the total rate of momentum change from collision, we must investigate the collision probability. So if the collisions are truly random, there will be a constant probability of collision at any time for each electron. If we are considering a random collision, there is a constant probability of collision for every electron. With the definition of mean free time between collisions, the probability that an electron has a collision in a time dt is given by dt by tau. So tau is the mean free time. That means the time between a particular collision. So we will tell the probability of collision for a particular electron in a time dt is given by dt by tau. Dt by tau is the probability for an electron to have a collision in a time dt by tau. So the differential change in momentum is given by dpx is equal to minus px into dt by tau, where dt by tau is the probability that an electron has a collision in time dt. So differential change in momentum is dpx is equal to minus px into dt by tau. So what is dpx by dt? Dpx by dt, that is rate of change of momentum due to decelerating effect, is given by dpx by dt is equal to minus px by tau, where tau is the mean free time. So this is the rate of change of momentum due to deceleration, and we have seen rate of change of momentum due to acceleration as dpx by dt is equal to minus nqex. So at steady state, when adding these two, the answer should be 0. So now in the steady state, sum of acceleration and deceleration is 0. So we can write, adding both equation, we can write minus px by tau is minus nqex is equal to 0, or average. What is averaging a certain thing means dividing by total number of things, right? So here we are averaging the momentum, electron momentum. So it will be px by n number of electrons. So the average momentum per electron is given by minus px by n is equal to minus tau into qex. You write this equation in a book, that time it will be clear step by step if you are writing. So average momentum minus px by n is equal to minus tau qex. Okay, here one mistake is there. Here minus is not there. Just consider that. If you are taking this equation, minus px by tau is equal to nqex. We need px by n. Px by n is equal to tau qex. Tau qex. That is minus tau qex. So here minus is not there. This is just px by n. Px by n is equal to minus tau qex. Okay, so what is the average velocity of an electron? Velocity of an electron is also known as drift velocity. What is the average velocity of an electron? So velocity of electron is nothing but momentum divided by mass. So average velocity is equal to momentum. Average momentum is px by n divided by effective mass. So momentum is given by, drift velocity is given by, since it is average, we are using this bracket, okay. So the velocity of an electron is given by minus tau qex divided by effective mass m star. Effective mass m star. In textbook you can see it as mn star, where n stands for n number of electrons. So actually the individual electrons move in many directions by thermal motion during a given period. But equation of this drift velocity tell us that net drift of an average electron is in response to the electric field. The drift speed described is usually much smaller than the random speed due to thermal motion. Next we are going to derive an expression for current density based on this drift velocity. Okay, so we know current is I. So current is I, and I by A is nothing but current density. Current by unit area is known as current density. So current density Jx is having x stands for this electric field is applied in x direction. So we have the notation of x here. So the current density Jx is equal to minus qn into velocity. This equation you might have studied in your earlier classes. Current density is equal to minus qn Vx. Since we are speaking about electron, we are using this minus symbol for charge, negative charge. So minus qn Vx. Here we are speaking about the unit. Current density is ampere per centimeter square, because current is ampere and area is centimeter square. So ampere per centimeter square is coulomb per electron, electron per centimeter cube into centimeter per second. Velocity unit, number of electrons, and charge, coulomb per electron. So this is the equation for current density. Jx is equal to minus nq Vx. Now we are going to substitute the value of Vx here. So we know what is Vx. Vx is equal to minus tau q Ex by m star. Minus tau q Ex by m star. So Jx is equal to, we have to substitute Jx value as minus nq Vx. So Vx is equal to minus tau q Ex by m star. Minus of minus will become plus, and we have q square. So tau n q square by m star into Ex. That is the equation for electric field. So you can see here the current density is proportional to electric field. That itself the Ohm's law tells. So we can simplify this equation and write as Jx is equal to sigma Ex. We are introducing a parameter known as sigma. That sigma is nothing but tau n q square by mn star or m star. This is nothing but sigma is equal to tau n q square by m star, where this sigma is known as conductivity. Conductivity is a property of a semiconductor or metal or anything. How much conduction it will be doing. Right. So sigma is equal to tau n q square by m star. So further we can write the same equation as nq mu n. nq mu n. So what is mu n? We are writing it as nq mu n. So from this equation, what is mu n? Mu n is nothing but q into tau by m star. Q into tau by m star, charge of the electron into mean free time by effective mass. So this mu n is known as mobility of an electron. Mu n is known as mobility of an electron. So mobility of an electron mu n is equal to q tau by m star. This is also equal to Vx by Ex. So you can see the same equation here from this Vx by Ex. From this equation, if you are taking Vx by Ex, what remains? Minus tau q by m star. So that itself is the mobility, Vx by Ex. So this also is Vx by Ex, ratio of drift velocity to electric field. Say a lighter particle have higher mobility. So you can see here effective mass is in the denominator. So if you are having lighter material, then the mobility is more. If you have a heavier material, then the mobility is small. So a lighter particle have higher mobility. Mobility describes the ease with which electrons drift in a material. How much easily an electron can move in a material is the measure of mobility. Mobility is a very important quantity in categorizing semiconductor material and in device development. Next we will move to one more small topic, effective mass. We have seen Mn star, right? Same thing, or M star or Mn star. When responding, example, to external forces, the effective mass determines how quickly a particle will accelerate. It can be either heavier or lighter than the true mass of an electron. It will be different from different energy bands. So we can say M star is equal to 1 by 3 into 1 by ml plus 2 by mt, where ml is the mass in longitudinal direction and mt is the mass in transversal direction. So just remember this equation. Effective mass M star is equal to 1 by 3 into 1 by ml plus 2 by mt. So here we have explained the conductivity and mobility in terms of electron as a charge carrier. The same thing will apply for holes also. Only thing what you have to change is the Q will be having a electron is having a negative charge, whereas holes is having a positive charge. Okay, then this n, number of electron n should be replaced with number of holes p, and electron mobility mu n has to be replaced with mu p. So if you are considering the total current density, we have to consider both. So see here, conductivity in a semiconductor. We are comprising everything and telling, in the presence of an electric field, electrons and hole both drift, but in opposite direction. Since charges are opposite, both current flows in the same direction. The conductivity due to each depends on how many carriers there are, n or p, n for negative and p for positive. How easily can carrier move? That is mobility, mu n for electron, mu p for holes. So when an electric field is applied like this, Ex, electrons will move in this direction and holes will move in this direction. So electric field, electrons and holes both drift, but in opposite direction. Since charges are opposite, the current flow will be in the same direction. Okay, so the conductivity of the semiconductor sigma we have given by mu into q into number of electrons, mu n into q n into mu n into q into n. So if you are considering both charge carriers, the conductivity of a semiconductor can be written as Qn mu n plus Qp mu p, where Q is the charge of the electron or hole, n is the number of electron, p is the number of hole, mu n is the mobility of electron, mu p is the mobility of hole. So the current density is given by sigma Ex. J is equal to sigma into Ex. We are still considering E in the x direction. This is the drift current. The direction of convention current is the direction of flow of positive charges. So the current flow, if electrons are moving in this direction, holes will move in the opposite direction, and that will be the movement of current flow. Current flow will be in this direction, right? So the conventional current is in the direction of positive charges. Holes flow along the direction of E, hence they create a current in the direction E, as holes are similar to positive charge. Electrons drift in the opposite to E. Electrons drift in opposite of electric field. Since electron have a negative charge, current due to this also in the direction of E. Hence the drift current of both electrons and holes is along the direction of the applied field E. The drift current is constant throughout the bar. So in this topic we learned about mobility and conductivity. So we can write the current density Jx as, for a semiconductor, current density Jx is equal to Q, charge of the electron or hole, into N mu n plus P mu p into electric field Ex. This is the total current density when applied an electric field in the x direction for a semiconductor.